Hello everyone, this is Xilun from Cornell University, and today I'll be presenting our TACL journal paper, Adversarial Deep Averaging Networks for Cross-Lingual Sentiment Classification. And this is joint work with Yu, Ben, Claire, and Kilian. So I assume everyone here is familiar with the task of sentiment classification, where we are given a piece of text and we try to predict the sentiment polarity of it. So the good news is we do have a wide range of models that are very effective to tackle this problem, and which are enabled by the availability of these large-scale annotated data sets, such as the Stanford Sentiment Tree Bank and so on. But this is not the end of the story, though. A big caveat here is that most of these labeled data is only available in English, and for most other languages, they do not enjoy such an abundance of annotated data, and leaves us the question about what we can do in this case. Well, an active research direction to tackle this problem is cross-lingual sentiment classification, where we try to utilize the abundant annotated data in a resource-rich source language in order to build or improve a sentiment classifier on a low-resource target language. Traditionally, people have been focusing on what's known as resource-based transfer methods, where they directly utilized some sort of cross-lingual resources, such as a parallel corpus or a machine translation system, in order to bridge the gap between the two languages. A good example for this is the previous state-of-the-art method for cross-lingual sentiment classification, which is this cross-lingual distillation method. So the basic idea of their method is they take the trained sentiment classifier on English and use that to make predictions on the English side of a parallel corpus. So then they could use the Chinese side of the same parallel corpus as pseudo-annotations in order to train a sentiment classifier on Chinese. So this is how they are able to achieve cross-lingual transfer by directly leveraging a parallel corpus. However, for many truly low-resource languages, even these parallel corpora may not be available to us. And therefore, we in this work try to reduce the need for such cross-lingual resources. And we hence propose this technique called language-adversarial training that only uses monolingual data during training. And the high-level idea is to learn these language-invariant feature representations that could better generalize across languages. Furthermore, we showed that our method significantly outperforms all previous methods, including a strong machine translation baseline, as well as the previous state-of-the-art system. Okay, so speaking of learning language-invariant features, the most straightforward idea we may have is through weight sharing. So here I showed a standard sort of an overview of a neural sentiment classifier, where it is conceptually divided into three parts. So we start with the word embeddings, and then we have a feature extractor that takes a sequence of input tokens and outputs a fixed length feature vector. And after that, on top of that, the sentiment classifier P will just look at this feature vector and predicts a sentiment label. So if we want the distributions of feature vectors between English and Chinese samples to be similar to each other, the simplest thing we can do is that we can just take this sentiment classifier trained on English data and use it to make predictions for Chinese samples. But unfortunately, as we observed in our experiments, this did not work well. So I'm showing a t-SNE visualization of some feature vectors of some random English samples shown in blue, as well as Chinese ones in red. So we see there is a clear dichotomy between languages, and we know that the feature distributions remain divergent between languages. And therefore, if we train a sentiment classifier on the English data, it will not generalize well to Chinese. So that did not work well. Well, now, if we actually had access to these parallel corpora, then our life would become much easier. So in this case, in addition to the standard sentiment classification loss, what we can simply do is that we can add a second loss that try to enforce the features to be language invariant. And since we have a parallel corpus, we can do this easily, right? So we can take a translation sentence pair from the parallel corpus, and here we can just minimize the distance between the feature vectors of English and Chinese sample. So this way, we can learn these language invariant features, and by combining these two losses, we are now learning these features that are both informative for sentiment classification and at the same time being language invariant. However, as I mentioned, for low resource languages, we may not even have these parallel corpora, and it leaves us the question like what we can do in this case, how we can achieve the same goal of learning language invariant features without having these parallel data. So this brings us to our method, language adversarial training. So as you can see here, we add another key component, the language discriminator Q, which is trained to predict the language of a sample by looking at its feature vector. On the other hand, the feature extractor F strives to prevent Q from being able to do so by maximizing the loss of Q. So therefore, this F and Q forms this adversarial relation to each other. And the main idea here is that if Q is not able to identify the language of a sample by looking at its feature vector, then the features we learned essentially capture very little language information and are hence language invariant. So this is how we are able to learn these language invariant feature representations with only monolingual data during training. Okay, so we plot a similar t-SNE visualization of the feature vectors, and we see that with language adversarial training on the right, we now have a much more mixed feature distribution. Okay, so let's dive a little bit more into the model details for now. So we start from the bottom, the input representation part. So here, a unique challenge for cross-lingual transfer compared to, say, domain adaptation is that we now have a problem of disparate input spaces. So what I mean by that is like two different languages, such as English and Chinese, they barely share any words at all. So they essentially have disjoint vocabulary sets. So our model needs a common input space to start with. So here we just use word embeddings to project words from two different languages into a low-dimensional vector space so that the models have a shared input space to start with. And we can simply use monolingually trained or even randomly initialized word embeddings for this, and it can work, so because the embeddings will get updated during training, but I will show some numbers in the experiments for this. However, if we want to achieve the best performance possible, it is better to use these pre-trained bilingual word embeddings that embed words from two different languages into a single semantic space so that if two words have similar meanings, they will be close in the embedding space, regardless of language. And in this paper, the bilingual embeddings we used were still trained using parallel corpus, but there are more recent papers that proposed ways to learn these cross-lingual embeddings in a fully unsupervised way. Okay, so moving up a little bit to the feature extractor, as I mentioned before, the feature extractor converts an input sequence into a fixed length feature vector. And in this paper, we just chose the simplest model that we could imagine, a deep averaging network or a ADAN model that just takes the average of the word vectors in the input sequence and pass that through a feed-forward neural network, and that's our feature vector. Of course, our adversarial training framework also works with other more sophisticated feature extractor architectures as well. So I will show some experiments on when we are using CNNs or LSTMs. Okay, so moving past that, after we have a fixed length feature vector, the remaining components P and Q are just standard multi-layer perceptrons. Okay, cool. So I won't have time to go into the details of the model training, but I have just one slide for those of you who are very familiar with the field and have been wondering, say, how is our model compared to domain adversarial networks by Gani et al. Well, the one sentence short answer is that the training is not the same. So the training of ADAN is inspired by Wasserstein, Gan. And we also do not use the gradient reversal layer as used by Gani et al. So here, in addition to the theoretical results we show in the paper, we also did a grid search on the two hyperparameters lambda and k that regulate the adversarial training part. So in the heat map, color indicates accuracy, and the redder it is, the higher the performance. So therefore, we see the ADAN training on the right not only gives a higher overall performance, it is also much more stable with respect to the hyperparameter selection. Okay, so now let's move on to experiments. So after showing the main experimental results, I will show the two experiments that I promised earlier on the choices of word embeddings as well as model architectures. So finally, if we have time, I'll briefly go over the semi-supervised setting. Okay, so in our main experiment, we evaluate ADAN against a range of different baseline methods for cross-lingual sentiment classification on two target languages, namely Chinese and Arabic here. So the first set of methods we compare with is weight sharing, as I mentioned before. So it is actually using the same bilingual word embeddings as used in ADAN, but we see that weight sharing does not give us a satisfactory result. Then we compare with domain adaptation methods because, in principle, cross-lingual transfer can be viewed as an instance of domain adaptation. But in practice, the distributional divergence between languages is much more significant than that in typical domain adaptation. So we see here a domain adaptation method also did not work well out of the box for our task either. And then a strong and commonly used baseline method is this machine translation baseline, where we use Google Translate to translate the test set from the target language into English, and then make a prediction there using the trained English sentiment classifier. So here we see it indeed performs better than the previous baseline methods, but still ADAN is able to achieve a much higher performance despite the fact that we are only using a tiny fraction of the parallel coppers as compared to those used in Google Translate. Finally, we compare with the previous state-of-the-art method, the cross-lingual distillation method that I mentioned before. So here we see again, ADAN significantly outperforms their methods on both languages. Okay, so now let's look at how do different choices of word embeddings affect the model performance. So here, the rightmost column is the bilingual word embedding we used in our main experiment. And the column in the middle just shows another choice of pre-trained bilingual word embedding. For the interest of time, I will just want to highlight one number here. So this is ADAN trained with randomly initialized word embeddings. So in this case, no cross-lingual resources were used whatsoever. And we can see that even that, ADAN is able to outperform some of the baseline methods that had access to trained cross-lingual embeddings. And this was a very encouraging find to us, and actually motivated us to further seek down the path towards truly zero-resource cross-lingual transfer. And we actually just had a paper submitted to iClear last month, so feel free to take a look if you are interested. Okay, so now let's look at the choices of feature extractor architectures. So we can see here, if we can afford our model running a little more slowly, then we are able to achieve a better performance than using a very simple DAN feature extractor. So my personal takeaway message here is that it seems a convolutional neural network is a good compromise point between effectiveness and efficiency for a text classification task like this. Finally, in practice, it is usually not that difficult to obtain at least a small amount of annotated data in the target language. And we wanted to ask whether our model remains effective with the addition of these target language annotations. So we see the answer is affirmative. So we started from adding 100 labeled samples in the target language, and we keep doubling that. And we see in this figure that the ADAN in green maintains a comfortable margin over the baseline methods, even when we add more than 10,000 annotated samples in the target language. Okay, so in summary, in this paper we proposed ADAN for the task of cross-lingual sentiment classification, where we don't have any training data in the target language. So our core technique is this language-adversarial training, which learns these language-invariant feature representations by only using monolingual data for training. And we compared ADAN with many methods, and we show that ADAN significantly outperforms all previous models in our experiments. Finally, a very encouraging find is that ADAN is able to outperform some of the baseline methods even when it is not using any cross-lingual resources. Namely, it is trained with randomly initialized word embeddings. Okay, so that's all I have today. Thank you, and the code is available online in GitHub.
Okay, so is there any question from the audience? Right, so basically, like in your approach, you kind of like trying to project features from different languages into the same semantic space, right? And then trying to sort of like identify those so-called language-invariant features.
Yep.
But in reality, I guess there might be like some features actually specific to certain language.
Right.
So have you actually like thought about like whether you could have something to separate these two? So like some.
That's a great question. Actually, the iClear submission we mentioned, we did exactly that. But that's more important when you have more than two languages. So like here, the hypothesis is that if you have two languages, yes, there are some of the features are shared across the two, and some are specific to both of the either of the language. And like in this case, for transfer learning, we hypothesize that only those shared features are the most useful for the transfer. But the case is like when you have multiple source languages, then both might be useful. Like for example, if you are transferring from English, Chinese, and Spanish to say German, and if you try to find a language invariant features across all four languages, those could be very sparse. But the fact that like German is much more similar to English means that we can probably utilize some sort of like language-specific features to English to help this transfer like process.
Okay, right. So in terms of next steps, so what would be your kind of sort of like a.
Yeah, sure, yeah. So I think something that we found was useful for cross-lingual transfer are those cross-lingual like language representations. So far, they are just word representations. Actually, I had another poster here at EMNLP on like unsupervised multilingual word embeddings. But still, those embeddings are currently just like token level like word embeddings. But we see those like contextualized embeddings like ELMO and other stuff happening in the monolingual case. So maybe I think it's good to go into the multilingual case on those language representation part.
Okay, thank you. So is there any further question from the audience?
Yes.
Thank you for your talk. I'm curious, we've also done work on cross-lingual sentiment analysis, and some of the things that we have found is that how well you can do transfer depends in part on the language family, in part on how close your training data is in genre or domain to your test, and also multi-source versus single source. You didn't talk much about your data, other than that it's monolingual, I guess.
Right, yes. So I think what you said are exactly right. We had the same feeding. My bad didn't have time to go into the more details of the data. I'll explain more. So here, the English training set is Yelp reviews. And the Chinese set are a data set of hotel reviews. So they are both reviews, but not exactly from the same domain. And for Arabic, it is, I believe, Newswire, but it's a sentiment data set, BBN sentiment data set in Arabic. But I don't read Arabic, so I forgot the exact detail of that. And for the monolingual part, yes, we use basically we use the sort of in-domain data with the test set. For training. We did see that if you try to use like not so different, like slightly different data, that could also work. But of course, there's a lot of things that could impact the performance.
Okay, so is there any other question? Okay, so if not, let's thank the speaker, and that's the end of our session.